Alright, we're entering the last section of 9.1 and it is a long lesson. There's a lot of content here. So we're moving on to other variations of graphing of these rational functions, and you'll notice now we have f of x is equal to 1 over x squared. So this is the first time that we see an x squared in the denominator. So let's think about different values that we could plug in for x and find out what we get for y. So I guess the first of all, I'm thinking what we've seen before, we've seen vertical asymptotes whenever the denominator is equal to 0. So if what values of x will give us a 0? Well, a 0 would give us a 0, and so the y value here would be undefined, and this is where we get a vertical asymptote, is right along x is equal to 0. Thinking about what other values we could have here, I'm going to put in a, oops, I'll get a pen. We could have a negative 1 and a negative 2, a plus 1 and a plus 2. Alright, so if we put in a negative 1 for x, what would we get? We would get 1 over negative 1 squared, which is the same thing as 1 over, now whenever we square stuff here, we're going to notice whenever it gets squared, regardless of whether we start off with a positive x or a negative x, after you square it is positive. So we're going to get 1 over 1, which is equal to 1. So at the end of all that work, really what we have here is a 1. So if I put a negative 1, I get a positive 1. If I put in a negative 2, I get 1 over negative 2 all squared. So that's going to be equal to 1 over 4. So if my x is negative 2, my y is 1/4. So you see how very quickly that gets smaller and smaller. And if we just think ahead, if we put in an increasingly negative value for x, so in other words, as x approaches infinity from the negative side, so as x gets exceedingly large negative value, y 1 over a very large number is going to get closer and closer to 0, but never quite get there. So we're going to get the asymptote right here. So right away I'm going to put in, we have an asymptote along here, and we can see that happening. Okay, so what about between this value and the asymptote? What if I put in a negative 1/2? So let's see if I can squeeze that in somewhere over here. So put a negative 1/2 in for x. So what would I get for my y value? Well, let's think. I get y is equal to 1 over negative 1/2 all squared. So that would be the same thing as saying y is equal to 1 over 1/4, and then when I multiply by that reciprocal, really I get a y is equal to 4. So when I put in a negative 1/2 for x, I get a 4. So you can very quickly see that asymptotic behavior. Now what happens when we put the same values in, but we put positive values in for x? If I put in a 1 for x, I'm going to get that 1 over 1 squared, so I will get 1 again. So an x of 1 and a y of 1. If I put an x of 2, I'm going to get 1 over 2 squared, so I'm going to get 1/4. And same thing as before, if I put in a plus 1/2 over here, I'll get a plus 4. So you see this up here somewhere. So again, we're going to get this kind of a shape here. This is a shape that some of us like to call a volcano. And we're going to be looking for that pattern. This line over here, it says, the factor of x has a multiplicity of 2. So what do we mean by that multiplicity of 2? So looking over here, this is the multiplicity of 2. It's the fact that it's squared. Therefore, the graph remains positive on either side of the asymptote. I just want to use that statement to just explain a little bit about this idea, about this multiplicity of 2. If I would graph y is equal to x squared. So there's an example where we say there's an x with a multiplicity of 2. And you remember how that looks. It looks like this, right? Okay, now if I graph y, I got a little jump there. If I graph y is equal to 1 over x squared, that's the one I just did. And so we have that one here. Wherever we have a 0 in my original one, that's where we're going to get the asymptote, right? Because whenever we have a value of 0 in the denominator, that's where we have the asymptote. And you'll look on either side of this is positive. So that's why we have this shape. You notice the shape profoundly changes, right? And it's not too surprising when when the y value here is something small, here the y value is large because it's the reciprocal. So the point I wanted to make is that our work before, thinking about, say, x plus 1 all squared, and this is going to have a multiplicity of 2, and so on. When we have a multiplicity of 2, it's either both positive, right, or another version would be negative x squared. They would both be negative. So when we have that multiplicity of 2, here it would be negative on both sides, here it's positive on both sides. Okay, so just maybe that helped, maybe it didn't, I'm not sure. So let's fill this in, let's figure out what is our non-permissible value. Well, that is where our vertical asymptote was at x, and x cannot be equal to 0. And looking at this, the easiest way to see that is to say, what are the possibilities of creating zeros in the denominator? We do not have an x-intercept, we'd say none. We do not have a y-intercept. The vertical asymptote is at x equals 0, and we do have a horizontal asymptote at y is equal to 0. The domain is that x cannot be equal to 0, and besides that, it's all real numbers. So to put it in nice notation form, we'll go like that. The range in this case, you'll notice that y is greater than 0, and besides that, it's all real numbers. There's my quick curly braces. Okay, so that's the first one. That's the volcano. You know what? I think I'll just do a quick switch into Desmos and do a couple examples. Alright, so here's 1 over x squared, graphed a little bit nicer than I could have done it. If we were to make another graph, and we'd say y is equal to 1 over it. Now in this case, I'm going to change it a little bit. I'm going to say x minus 3 all squared. Then you'll notice the difference between my original blue graph of where the vertical asymptote is at x equals 0, and my new one, the green one. All it does was shift it over to the 3 to the right. So you can see that we can apply the things that we learned about translations to all our other graphs. So now if I say add, I don't know, plus 2 on it, you can see how it moved up 2. So we've learned this y is equal to 1 over x squared, the volcano, but really we've learned a bit of a family of shapes. Now looking at example number 2, you might think that this is just the same family but moved over 4 to the right, but be careful, this is not the same as y is equal to 1 over x minus 4 all squared, right? This is different, not the same. Okay, so this would be what we just did, but moved 4 to the right. This is something that's completely different. For this one, for the one that's a family, we would have a multiplicity of 2, and we would get a 0 in the denominator whenever x is equal to 4. So in this one we would have a single asymptote at 4. So here, once we have factored the denominator, and here's the first step, you can recognize this is a difference of squares. We have an x plus 2 and an x minus 2. So what we're going to get in this one, we have two different ways of having an asymptote, of having zeros. Here we would have, we're going to get a 0 whenever x is equal to negative 2 and wherever x is equal to plus 2. So these are the vertical asymptotes. So right away I can put a minus 2, oh actually I'll put it over here. Right away where I have the minus 2 and the plus 2, I'm going to put these vertical asymptotes. See if I can fit it in here. Okay, so it's a little bit different than what we've seen before. Now, why don't we try to figure out what our x-intercepts and our y-intercepts are going to look like. So why don't we go and, why don't we go and take a look at our x-intercepts and our y-intercepts. So again, our x-intercept is what's the x value when y is equal to 0. So if I were to plug this in, and I would just say y is equal to, and I can either use my original version or my factored version, but I'm gonna use the factored version here is 1 over x plus 2 times x minus 2, and I'm going to put in a 0 here, 1 over x plus 2 times x minus 2. Is there any value that I can put in for x so that I can get a 0 for my y? There is no way that I can do that. So even if I put a 0 in here, I'm not going to get it. If I put a -2 or a +2, I get an undefined. So there, under x-intercept here, I'm going to say none. And I can actually put in here my non-permissible values. Those are my vertical asymptotes. X cannot be equal to -2. X cannot be equal to +2. Now thinking about my y-intercept, so my y-intercept is when x is 0, what is y equal to? This is a lot easier, isn't it? If I go and put y is equal to 1 over, well, 0 plus 2 times 0 minus 2, that's the same thing as 2 times -2, so that's -4. So it's going to be -1/4. So here I'm going to put in a value of 0, -1/4. And I can go and put that in right away, where my x is 0 and my y is -1/4. So it looks like about right there. So I'm going to say 0, -1/4. Okay, so my vertical asymptote, I really have two of them here. X equals -2 and x equals +2. Now the next thing we're going to look at is there a horizontal asymptote. So really the horizontal asymptote, we're wondering what happens when x gets very negative and very positive. So if we consider our values here, and let's just make kind of an x and a y grid here. So if I was to look at my x squared minus 4, if I put some very large negative value in there, I don't know, let's say if I put -100, what do I get for my y value? I get 1 over -100 squared minus 4. So first of all, this -100 turns into a positive, works out to 10,000. 10,000 minus 4 is equal to a positive, what, 9996. You don't actually have to do the math, but you realize even if I put in a very large negative value, I'm going to get a 1 over a very large number. So really what this works out to is a small positive number. So looking over here, what does that mean? As my x gets increasingly negative, and we've seen this pattern before, I'm going to get closer and closer to 0. So what I can say here as is there a place to put it down here? Explain the behavior. So I can say as x gets closer to -infinity, y gets closer to 0. All right? And here I go, so I'm going to put that in there. So it's going to look a little bit like that. Now, looking at the asymptote, we realize that there is no, it's not going to be crossing the x-axis anywhere. So I know that it's going to take this shape like that. Okay, and I guess if I check for the other, from as x gets very, very large, so we'll do a second example. If I'm going to say x is equal to +100 now, and I will get the exact same thing. I'll get 1 over a very large number, in this case 9996. So again is equal to a small positive number. So as x gets very, very large, the y value gets closer and closer to 0. So it's also going to look like this. And it hits that asymptote and goes up like this. So these two sides look the same. And then all we got to do is wonder what's going to be happening in the middle. So for the middle, I think what we need to do is just pick a couple tests. So let's pick -1 and +1. So over here we've done a couple. Here, I'll make some space for us. What happens if I put in another x value of, say, -1 and +1? So looking at, it might be easier if I say that x squared minus 4. So I'll go 1 over -1 squared minus 4. That's equal to 1 over 1 minus 4. So that's equal to 1 over -3. So it's -1/3. So when x is equal to -1, y is equal to -1/3. So it looks a bit like this. So -1, -1/3. When x is equal to +1, and because of that squared, we're going to get exactly the same number. again, negative 1/3. So looking over here, when x is equal to positive 1, x is equal to, or y is equal to negative 1/3. So there's really not too many options of where that line is going to go, because we know it's going to hug up next to that asymptote, so we're going to get a sketch that looks like this. And again, this is a pattern that we are going to see more often. So how to recognize the pattern? So when we have in the denominator a difference of squares, in fact just an x squared minus any number, in this case it's a clean difference of squares because it's plus 2 and minus 2, but if that 4 wasn't a perfect square, if it was just anything, so if we had 1 over x squared minus some number here, then we get this pattern. And so the pattern that we call this one, I think, is called a driveway. Not exactly sure if it's the perfect name, but I think it's from the asymptotes. You can sort of see here is a picture sort of a driveway, and we get these shapes afterwards. I should draw in the fact that we do have this horizontal asymptote as described. So let's say that we have a horizontal asymptote, as I just mentioned, at y is equal to 0. The domain, so what can the x values be? The x can be anything except it can't be negative 2 and it can't be positive 2. So I'm going to say x is not equal to negative 2, x cannot be equal to positive 2. Otherwise it's all real numbers. Okay, and there's my domain. How about for my range? Here my y values can be anything except for 0. So I say y is not be equal to 0, but y otherwise can be any of the real numbers. And I'll make it look a bit more like set notation like that. It says explain the behavior of the graph near the non-permissible values. So as x approaches negative infinity, y approaches 0, and also as y approaches positive infinity, y is also approaches 0. And we'll notice that it's, in this case, it's from the positive side. So if I had a horizontal asymptote here, in this case both of them are coming from the positive side. If it was from approaching from the negative side, it would look more like that, right? So we could get that kind of a pattern in different questions. What about close to negative and positive 2? So we can say as x approaches positive or negative 2, then y approaches infinity. Okay, and in both cases it's downwards, so it's going to be negative infinity. Okay, so maybe we can commit that one to memory. If you see a pattern that looks like that, 1 over x squared minus some number, we're going to get this driveway pattern. Okay, and just a reminder, sort of like what I was saying before, if we think of y is equal to x squared minus 4, what does that look like when we graphed it? Well, remember y is equal to x squared looks like that. Okay, so if I was to say what happens if we do minus 4, we end up getting something that looks like this. Okay, wherever we get these zeros, when we do y is equal to 1 over x squared minus 4, those two places, minus 2 and plus 2, become our asymptotes, and you'll see all these values are negative, so although it's a reciprocal, they still stay negative, and that's why we get this shape here. And all these values are positive, so that's why we get this shape that's positive, and these values are positive. So sometimes if you look at when you're given this and you think, oh, what does x squared minus 4 look like, and just think wherever there was a 0, that's where we get an asymptote. Positive values are still positive, negative are negative, and then recognizing that it's a roadway and you have these asymptotes, you know, there's only so many ways you can fill in the numbers. You can fill it in this way, right, or you could fill it in this way, depending on whether you have positive or negative values. So I hope that quick little sketch or thinking about this helps a little bit. We should go along to example number 2, and this one looks a little bit different. It says sketch this one here, but remember to factor first. So when we factor this, looking at the denominator, factoring x squared minus 6x plus 9, it works out to 1 over x minus 3 times x minus 3, because we have two numbers, negative 3 and negative 3, when multiplied together give us a positive 9, and when added together we get a minus 6, so that works out. I won't forget my plus 2 that's tailing off at the end. In fact, instead of writing x minus 3 times x minus 3, it kind of makes more sense to write x minus 3 all squared. And then suddenly I'm thinking, here's what I'm thinking, I'm thinking volcano, because this looks a lot like my y is equal to 1 over x minus some number all squared, right? So the previous example we did, I think it was x minus 4, and that was a nice little difference of squares, or a nice little x, sorry, that was a nice thing to be able to graph. Here we're going to get a volcano, and so we will get an asymptote where x is equal to 3, right? So if I go over here and I look here, x cannot be equal to 3, so I'm going to get this vertical asymptote right over there. And the difference here is I've got this plus 2, so that means it's going to be going up 2. So I will have a horizontal asymptote right here. And what's the volcano shape? If you recall, if we had like y is equal to 1 over, say, x minus 2 all squared, at 2 we had this shape over here, right, moved over like that. So here we're going to have over 3 and up 2, and it's always positive. We always have this positive shape. So right away I'm anticipating, I'll erase it in a second, but I'm looking for this kind of shape here. But we just need to have a couple of values. So let's make an x and our y table of values and think about what we might get here. So an x and our y. So first of all, I guess a 0 would be interesting to find out. So if I put in a 0 over here, it's like putting a 0 in right there. So 1 over, well, negative 3 squared is a ninth, plus 2, so I would get 2 and 1/9. What if I put in a 1 here? So if I change this x value here and I put in a 1, 1 minus 3 is minus 2. Minus 2 squared is 4, so I would get a quarter, plus 2, so I would get 2 and a quarter. What happens if I would to put a 2 in there? Okay, well, let's just put a 2 in there, so I get 2 minus 3 is minus 1. Minus 1 squared is 1. 1 over 1 is 1, plus 2 is 3. So let's do these three values to begin with here. When x is 0, here I'll erase my previous mess here. When x is 0, y is equal to 2 and 1/9. So here I'll put 0, comma 2 and 1/9. When x was equal to, what was it again, 1, then I had 2 and a quarter. Boy, it's hard to get that just right. When x was equal to 2, then I had 3. What about if I put in x equals 3? Well, if I put in a 3 over here, wait a minute, that was my non-permissible value, because 3 minus 3 is 0, 0 squared, and I have a 0 in the denominator. So this is my undefined value here. What if I put in a 4? So if I put in a 4 here, I get 4 minus 3 is 1, 1 squared. It's going to be the same value as when I had this, great, because 2 minus 3 was negative 1, negative 1 squared is 1, 4 minus 3 is positive 1, positive 1 squared is also 1, so I get 1 over 1 plus 2, I get 3. So we're going to get that same, that's that volcano going up and then back coming down again. So over here I'll put a 4 and a 3, and then my 5 would come down like that too. So here is my sketch. It goes way up like this, and then it comes down, goes like that. Okay, so filling in these values, my non-permissible value, x cannot be equal to 3. My x-intercept, it doesn't cross the x-axis anywhere, does it? So I'll say none. My y-intercept, I figured it out, was at 2 and a 9th. My vertical asymptote is at x equals 3. My horizontal asymptote is at y is equal to 2. The domain here is that x cannot be equal to 3, but it can be anything else. So x such that, curly brace, there we go. My range, while looking at all the y values are greater than 2. Y is greater than 2. Y such that. Okay, and scribblies over there. And some of you might actually notice and say, hey, I think, if I put an X back over there, I think I just looked at that, and it was purely, folks, by accident. Before when we were playing around in Desmos, that's the one I threw in there, and it is actually my x minus 3 and plus 2. And I said, just check that out, how it moves 3 to the right and 2 up from our, see, that was our original one. 1 is equal to x squared. And here this the green one moves 3 to the right and up 2. So Desmos doesn't draw in the asymptotes, unfortunately, but that's how it looks. Alright, now looking at our last example, and I know it has been a long video, so I'll try to make this kind of quick. This looks a little bit different than what we've seen before. This is not 1 over x squared minus 1, and it is not 1 over x minus 1 all squared, right? Because this is a variation of the first one that we got, and this is a little variation we've seen before. So this is something different, and you'll notice what's different here is that there's no way that we can get a 0 in the denominator. You cannot pick an x where if you pick a number and then square it and then add 1 to it, the smallest we can get in that denominator is 1. Because if you pick a negative value squared is positive, right? So another way to say this is this down here is to say that x squared plus 1 is always positive. Another way to say that it is not factorable. There's no way you can get a 0 out of it. You can't factor x squared plus 1 into, say, x plus 1 or x minus 1. It just doesn't work. So in either case, when x gets very large, either in the positive, approaches positive infinity to the right, or negative infinity on the left, y is going to get smaller and smaller. So the first thing I want you to notice is that we get this kind of pattern again. Okay, so we're going to get this asymptote, a horizontal asymptote at y is equal to 1. We just fill that right in here at or y is equal to 0, pardon me. We have that horizontal asymptote. But what happens in the middle? Is it going to be a volcano, or is it going to be something else? Well, if you recall the volcano, there is a vertical asymptote. Oops, not very good. There's a vertical asymptote. In this question, we don't have any zeros, right? So the fact that there's no zeros means there will be no vertical asymptotes. Okay, so what are we going to get? Well, this is just going to come up, it's going to hit something, and it's going to come back down again. So let's do a quick table of values and try this out, and just pick a few numbers here. So we'll do an x here, and we'll do a y, and let's pick some large negative, like a negative 100 to begin with. If I put a negative 100, let me do my 1 over x squared plus 1, y is equal to, so if I put a negative 100 in here, I end up all together in that denominator getting 1 divided by something big, a big positive. So here I get a small positive number. And that's really this asymptotic behavior. That's what this approaches the x-axis, okay? How about if I put in a negative 1 and a 0 and a 1, and then if I put a plus 100, same idea. If I put a plus 100 here, I'd still get a very large positive value in the denominator. So again, I get a small positive, and that's where I'm going to get this same pattern over here. Okay, so what about negative 1? All right, so let's put a negative 1 in here. So negative 1 squared is 1. 1 plus 1 is, so I get a half. And not too surprising if I change this to a plus 1, because when I square it, I will still get a half. How about if I put in a 0? So if I put a 0 here, oops, sorry, if I put in a 0 squared is 0 plus 1, so I get a y value of 1. So let's put these in here. So a negative 1 for x gives me a half for y, a 0 gives me 1, and then a 1 gives me a half. So I was getting a little bit too ambitious here about this, so really it comes along, it goes up just a little bit. It's really not a very exciting one here. I'll put that one up there. So you're going to think it's going to be a volcano, but no, it's not a volcano. It just looks like a little hill. And what we sometimes call this is a snow-covered volcano. It could have been a volcano, except there's no zeros in that denominator. A volcano, not volcanoes. Are there any non-permissible values? Are there any numbers that we could put into this function that we would break math in the sense that we would have a division by 0 or a square root of negative? No way, there isn't. So all values are permissible. All x's can be put in there, so I would have to say none here. Is there a place where it crosses the x-axis? No, there is no x-intercept. Is there a y-intercept? Sure, there is, right there. At x equals 0, then y is equal to 1. The vertical asymptote, there is none for the vertical asymptote. For the domain, what can all the x values be? Well, since we don't have any non-permissible values, it's the easiest one we can write here. It's that x can be all real numbers. And how about for the range? We can say that, well, it's a very tight range here, isn't it? It's that y is going to be greater than 0. So I'll say 0 is less than y, but it has to be less than or equal to 1. All right, and we'll say we'll make this one a really nice one. Okay, so that's the set notation way to write it. We could do interval notation for something like that. We could say 0, comma 1, and then put this bracket here. So this one corresponds to the fact that it doesn't include 0, but it does include 1. So this is like, notice how much faster interval notation is than set notation. So describe the end behavior of the graph. I'm just going to say that as x gets closer and closer to either positive infinity or negative infinity, what happens with y? Y approaches from 0, and both times it approaches 0, it gets closer and closer to 0 from the positive side. A little messy there. Positive side. Sorry about that mess. Hopefully you can read that. All right, we are almost near the end here, so there's just a little bit of some shortcuts. You know what? The horizontal asymptotes, I'm going to say, let's not even worry about that. I don't think we're going to have any horizontal asymptotes. So this is like just for your interest if you're wanted to get into horizontal asymptotes, or if for some reason there's a textbook question that goes and talks about horizontal asymptotes, you can come back and read that. I've filled this in. Horizontal asymptote here is 3 over 5. This one I wrote really messy is equal to negative 1 over 3. This one's 0, 0, none, and none. So it's a quick little, actually, tell you the truth, horizontal asymptotes, they are a little bit handy, so let me back up. It says if the degree of the numerator equals the degree of the denominator. So what does that mean, the degree of it? So if you look at the highest power, so this is degree 2 and this is degree 2, that's why it's equal, because the 2 is equal to the 2. Then the equation is this ratio. So we take the 3 over 5, this 3 over 5, and that's where this 3 over 5 comes from. Okay, so looking at this example over here, I erase my mess here. So looking at this example over here, the term with the highest power is this one. It's a 3 and the 3. So since they're a tie, we're gonna go and say take the negative 1 from here and the 3 over there. So the horizontal asymptote, pardon me, is going to be at, horizontal asymptote will be at y is equal to negative 1/3. So what would that look like here? Y is equal to negative 1/3. You'd have that horizontal asymptote right there. If the numerator is less, so we've seen a few examples of that, then the horizontal asymptote is equal to 0. So in this case, the horizontal asymptote is 0. Here you have an x in the numerator, but x cubed. So the numerator power is of 1. 1 is less than 3. So again, we have a horizontal asymptote at y is equal to 0. Now, sometimes we get one where the numerator is greater, and then there is no horizontal asymptote at all. So y is equal to x plus 9 over 3, and so on. Okay, here's a little bit of a summary of the names that we've been giving things. this one was called the split. That was our first one. Now this is the one that you should really know. Okay, so all that stuff that we did in the beginning, if I just pop way back over here, this kind of stuff, you know that really well, and being able to do those practice ones that we did, these sketching, please know how to do that really well. See if I can get back to where we were. These other ones, the volcano, the driveway, and the snow-covered volcano, not as likely that you'll be asked to graph that without any technology. You might be given a calculator, in which case you could plug in some x values, just like we were plugging some in, but I think it's a quick little key. Here is your homework from the textbook. Please enjoy. It's kind of a new topic, these graphing the rational functions. Hopefully you'll get the hang of it, and as always, I will see you in class.